Welcome to lesson 10.06. Here we're going to look at separable differential equations and their relationship to exponential growth and decay and some other real-world contexts. Alright, so let's start here. Let capital B be the number of bacteria in a dish at any time t. First question, what does dB dt represent? So nothing earth-shattering here. dB dt represents the rate at which the number of bacteria changes at any time t. And if you think about bacteria, unless you actively try and kill it, it's going to continue growing. And so you might say this is the rate at which the number of bacteria grows. And this leads us to this question here. So consider the two differential equations, the two different equations written here for dB dt. These are, of course, differential equations because they involve a derivative. So the question is, what does each mean about the way that the bacteria is changing, about how the number of bacteria grows, and which one seems more realistic? So just take a look at each one in turn. It actually might be easier to start with the blue one here, but either way, just as simply as you can, what does each one tell you about the growth of the bacteria? All right, so let's start with the blue one here, and this is very clearly a constant rate of change. This is saying that the number of bacteria is always changing by 150 bacteria per unit of time, whatever that is. And we know that a constant rate of change is the characteristic of a linear function, right? It's always going to have the same slope, changing by the same amount at every instant. And so we could pretty clearly see this by solving this differential equation for a particular solution given an initial condition, and we would see a straight line, right, with a slope of 150. The more interesting differential equation is this green one here. So take a second and think about what this is telling you about the way that the number of bacteria changes. So you may recognize this as exponential growth, and if not, that's okay. What you want to understand is what this means. So this is saying that dB dt, the rate at which the number of bacteria changes, is exactly equal to 3 times b. And b is the number of bacteria in the dish at any time, which means something pretty incredible, that the rate at which the bacteria change is directly dependent on how many bacteria are in there at that moment. And this kind of makes sense. If you consider how each individual bacteria can spawn new bacteria, then the more bacteria you have, the faster it will be able to grow, right? Think about a population of rabbits, for example. The more rabbits you have, the more opportunities there are for them to have new baby rabbits. And so the more rabbits you have, the faster the population is going to grow, of course, until they run out of food and they start dying. But for our bacteria, in this purpose, it's just going to continue growing, according to this, forever and ever and ever. And it's going to grow by more and more and more. And this is the characteristic of an exponential function, right? The slope gets steeper and steeper and steeper. If you're wondering what I'm talking about, go take a quick look at the graph of e to the x, and you'll see exactly what I mean. And what's really interesting about this is that now that we understand how to solve differential equations, we can take this differential equation that's very simple and explains a really simple characteristic about the way that this bacteria is changing, and we can use it to now find a function, a particular solution, that will tell us the amount of bacteria at any time t. So let's go ahead and do that. Let's assume that there are 100 bacteria in the dish at t equals 0. So that's your initial condition. Solve both differential equations separately to find two different functions for b of t. Do they make sense considering how we characterized the growth in part b? So go ahead and do that, and I think you'll know exactly what to expect for each one, and so you can kind of tell whether you're on the right track or not. Go ahead and start with the blue function here. All right, so we'll start with solving the differential equation dB dt equals 150. This is, of course, a very simple separable differential equation. I separate the variables and integrate, and that will give me b is equal to 150t plus c. And using my initial condition, I solve for c. It's 100, not surprising. And this gives me the linear function b of t is equal to 150t plus 100, which should make perfect sense. Now we want to move on to the more interesting situation, the more realistic situation, which is solving this differential equation. So give it a try on your own first, and we'll take a look at it together. All right, so to start off, I'm going to separate the variables, and notice I can leave the constant over here on the right and just bring the b, which makes it much easier to anti-differentiate. And taking the antiderivative of db over b is natural log of the absolute value of b, and this antiderivative is just going to be 3t plus c. So now I'm going to use my initial condition to solve for c. So solving for c here using the initial condition, I get c equals natural log of 100. I'll just leave it like that and see why. And we need to unlock b from the natural log. So if I raise e to the power of each side, I will be able to get b all by itself. And got to be careful here, I'm taking e and raising it to the 3t plus natural log 100. That whole thing is the exponent. So on the left side, I'm going to have simply the absolute value of b. And on the right side, I want to notice something. If I am adding exponents, that means that I can rewrite this as e to the 3t times e to the natural log of 100. Because when I multiply with the same base, I am adding exponents. Well, what's e to the natural log of 100? Well, it's pretty simple. Natural log of 100, what must I raise e to the power of to get 100? And if I raise e to that power, I'm going to get 100. So this is simply going to be 100 e to the 3t. Now let's think about this for a quick second. B is the population of bacteria, and it starts off at 100, and the rate at which it's changing is always going to be positive because it's going to be 3 times b. And you could also just take a look at the function we have. This is never going to be negative, so b is always going to be positive, and therefore we can get rid of the absolute value and write our particular solution. B of t is 100 e to the 3t. Now let's check to make sure that these satisfy our conditions here. The initial condition is really simple. E to the 0 is 1. So when b is 0, we just have a population of 100. That's exactly what we said. And what I want you to also do is check that the derivative of this is the derivative we started with. So go ahead and take the derivative of this, and we'll see how it ends up being exactly what the differential equation that we started with. So b prime, I'm differentiating this equation here. Factor out the constant, and the derivative of e to the 3t is going to be 3 e to the 3t because of the chain rule. So what I'll end up with is 100 times 3 e to the 3t. Now remember, I wrote my differential equation. It was in terms of b. Well, we know what b is. B is 100 e to the 3t, and if I rearrange this, I'll see I have exactly that. So b prime, I'll rearrange, I'll have 3 times 100 e to the 3t. And guess what? 100 e to the 3t, that is the value of b at any time t. So the rate of change, b prime, or another way of writing it, dB dt, is exactly 3b. And that, of course, is the differential equation that we started with. All right, a couple things we want to take away here. The first is that I understand what a constant rate of change is, what that looks like, and what will happen when I find the particular solution to that. That shouldn't have been really that groundbreaking. But also what an exponential rate of change looks like, that it's proportional to the amount that there currently is, and that we can find the particular solution to that, and that it's going to be exponential, obviously. So let's go ahead and just dive in a little bit more and look at the definition of exponential growth and decay. All right, so here is the law of exponential change. A variable y, usually it's an output, y, grows or decays exponentially if it changes at a rate proportional to the amount present. In other words, its current value. That's really basic when we represent it as a differential equation, because the rate of change then is just going to be k, some constant, times the amount that's currently in there, y, where k is called the constant of proportionality. And k determines how fast y, your output, is going to be growing or potentially decaying. So there are a couple options here for k, right? In the first example, in the discovery problem, we saw when k was 3, right? dB dt was 3b. But k could also be 0, which would mean this whole thing would be 0. And if k is 0, y will be a constant. Now that should be pretty clear. The rate of change will be 0, so the value of y will never change. If k is greater than 0, we just saw this, y will grow exponentially. And as you might guess, if k is less than 0, so for example like negative 3y, well in that case the rate of change would be negative, right? And that means that our population, our amount, is going to decay exponentially. Now, what's really nice about exponential growth and decay is how relevant they are to real-world situations. Populations obviously grow proportionally to how much is in the population at the current time. And so you can model a lot of population dynamics with exponential growth. And substances, particularly like radioactive substances or certain chemicals, stuff like that, decay over time if you leave them alone. So it's got a lot of real-world application. What's also really nice is how simple the differential equation is, right? And so you can really clearly understand the growth rate of some situation with a pretty simple differential equation. And because we can separate the variables in the differential equation, we can actually use our methods to find a particular solution. So let's go ahead and do this now. Let's solve the differential equation dy dt equals ky in general, letting a sub 0 be the initial amount, or our initial condition. So go ahead and try this on your own. You should be able to do it just fine. If you need to look back at the discovery problem for a little guidance, go ahead. And then we'll take a look at the general solution together. All right, so we're going to go ahead and separate the variables, and now we're going to take the antiderivative of both sides. Now, the left side, pretty simply, is the natural log of the absolute value of y. And since k is a constant here, we can really just think about factoring out k, and the antiderivative of 1 dt is just t. So we're going to be left with k times t, and then we've gathered the constants of integration onto the right, and we have this plus c. At this point, we're going to use our initial condition to solve for c. Doing so leads us to c is equal to the natural log of a sub 0. Notice that I don't have absolute value signs here because I'm dealing with an amount of something, and so this situation would only make sense if a sub 0 is a positive value. I don't think you'd want to start out with a negative amount of a substance. Alright, so at this point we can put c into our equation and solve for y. In order to do so, I'm going to take e and raise it to the power of both sides. That will allow me to isolate y. Doing so allows me to simplify the right side quite a bit. Since I'm adding these two components in the exponent, I can rewrite it as a multiplication of e to the ln of a sub 0 and e to the kt. And e to the ln of a sub 0 is, of course, just a sub 0. Now notice here that since a sub 0 is positive, and e to the kt, no matter what the exponent is, e to any power is always positive. So this is always going to be positive, and therefore we can just sort of get rid of the absolute value sign, because y will always be positive. We won't need to take the absolute value. And this leaves us with our particular solution of y equals a sub 0 times e to the kt. Quick note, a sub 0 is sometimes denoted as y sub 0. I think they do that in the book, and that just denotes the initial y value, which I've just used an a here because we're usually dealing with some sort of amount. Now, you don't need to memorize this equation. What you want to do is make sure you understand the process by which we solved this differential equation. And if you do so, then no matter what type of an exponential differential equation you're given, you'll be able to find a particular solution. And it might, of course, be helpful to have an idea of what it will look like in the end, but there's no need to memorize this, simply to understand the process by which we got there. All right, let's take a look at an example that deals with exponential decay. All right, so go ahead and try this problem out. This is actually dealing with something called half-life, and when something is decaying, a half-life is the amount of time it takes for half of it to decay, not surprisingly. So go ahead and copy down the important pieces of this question here and complete part A and then part B. Try both on your own and we'll take a look at them quickly together. Alright, so here is the particular solution, A of t. Separate my variables, anti-differentiate both sides, solve for c, ln 70. Then I'm going to raise e to the power of each side. That gives me a of t is equal to 70 times e to the negative 1.5t. You can take a look back at some of the previous work we've done to see how this simplification works if you need a reminder. And this is always going to be positive, so I don't need the absolute value signs anymore. Alright, so this was easy enough, but the question that we really want to answer is, what is the half-life? In other words, how long will it take for half of the substance to decay? So think about how you would answer this question, set up an equation to do so, and go ahead and try and get the answer on your own before you press play. We'll take a look at it together. Alright, not too tricky of a question here. We want to know the time it will take for half the substance to decay. And if we start with 70, half of 70 is going to be 35. In other words, we'd like to know what t value will make a of t half of 70. So let's set up our equation. Doing so will leave me in a situation that looks very advantageous. This will allow me to solve for the t value that will cut the amount of substance I have in half. Go ahead and solve this on your own. We'll take a look at the solution together. So first move I'm going to make, I'm going to divide by 70 on both sides. This leaves me e to the negative 1.5t equals 1/2. And now I'm looking to isolate t, so I'm going to take the natural log of both sides. So on the left side, pretty straightforward, negative 1.5t. Natural log of 1/2, when I'm dividing inside the natural log, I can subtract outside. So natural log of 1 minus natural log of 2. Natural log of 1 is 0. So I have 0 minus natural log of 2, which leaves me with negative natural log of 2. And now I'm going to divide on both sides by negative 1.5. And doing so allows us to solve for the half-life, the time it will take for half of our substance to decay, which is going to be negative natural log of 2 over negative 1.5, which is approximately 0.46 years, about half a year. Now the piece that you really want to tune into is this right here. Notice what went into creating this. We end up with negative 1.5, which is our k value, and we have negative natural log of 2. The negative natural log of 2 was formed because we were taking the original amount, a sub 0, and cutting it in half, right? And so whenever we take the half of our original, we're always going to end up with a division that creates a 1/2, right? Even if this was 1,000 and this was 2,000, when I divide on both sides by the original amount, I'm going to get 1/2. So I'm always going to get negative natural log of 2, and I'm always going to end up with negative 1.5 when I multiply on both sides, if that is my k value. So really, no matter what my original amount of the substance is, my half-life is only going to depend on k, right, which is our constant of proportionality. And that should make sense because k is what determines how fast my substance decays. So obviously the half-life is going to depend on k. And in general, we can always use this to find the half-life, negative natural log of 2 divided by k. K is going to be negative, and that will give us a positive half-life. And so let's go ahead and just quickly jot that down so that we can remember. So if I'm dealing with exponential decay, which means my differential equation will be ky, where k is going to be negative, that's important to remember, then the half-life is simply going to be the t value that is equal to negative natural log of 2 over k. Remember, k needs to be negative so that our t value ends up being positive. You don't need to memorize this. It's helpful to know, but you don't need to memorize it at all. You just want to remember and understand the process by which we found the half-life so that if you needed to, you could do this again. All right, at this point, go ahead and move on to the homework on Math Excel.